Section 8.5 is going to continue this idea of proving triangles that are similar. Now, up to this point, we've proven triangles are similar. We could prove it by the definition, which basically means what?
That all of the corresponding angles are congruent and all of the corresponding sides are proportional.
Okay. Then we learned a shortcut.
We learned angle-angle similarity. So all we needed were two angles of one triangle being congruent to their corresponding angles in another triangle.
Perfect. So that was really nice. It was literally two things we needed to know super quick. Well, today we're going to learn two more ways to prove similarity in triangles. And these will involve sides, where angle-angle similarity, you don't need to know anything about the sides.
Correct.
So the two that we're going to learn, both are theorems. And again, both are kind of shortcuts. That's what's kind of nice about it. This is called the side-side-side similarity theorem. And we do have a shortcut of saying it. Now notice it has the similarity symbol. So if we leave that off, it actually is dealing with what?
Ooh, congruence. Because we talked about side before when we did triangles congruent. So we need to make sure we have that similarity on the end.
Okay, so hopefully, even just knowing the title of this theorem, hopefully you're thinking, okay, it's dealing with probably all three sides of one triangle compared to the other three sides of the other. Now, what do we need to know about those sides? Well, it says if the lengths of the corresponding sides of the two triangles are proportional. Now, what does that word basically mean?
That all of the ratios are equal. So, ratios of a corresponding side.
So they're going to have the same ratios in a sense, right? Then the triangles are similar. Okay, so in this example, I drew out the triangle so you could easily see the things that match up. It's not always going to be that way, so we'll kind of do an example of that in a little bit. So if I give you the ratio of AB to DE, so they're saying those are the two corresponding sides. If that ratio is the same as BC to EF as well as AC to DF, notice three ratios that are equal. All right, again, it says if the corresponding sides, so all three sides of one triangle compared to the other three sides of the other, are proportional, then we can say the triangles are similar.
So really, we're starting off with if we have the statement of proportionality,
exactly,
then we can say that the triangles are similar.
Exactly.
We need nothing with angles.
And that's what's kind of nice about it.
Cool.
Now, if I know the triangles are similar, then we could then say the corresponding angles are congruent. So we could go beyond. But a lot of the questions are just going to ask you to decide if they're similar or not. So a lot of the things you're going to hear us say today is when we start the question, think about what is it they're giving you. So what postulate theorem would actually be logical for that particular problem? All right, let's talk about the other one, Ms. Hooker.
All right, the other one we're going to focus on today is side angle side similarity, or SAS similarity. And if you hear it again, just listening to the word side angle side, we've seen that before with congruence, where we know we talked about the included angle. Same thing here. So it says if an angle of one triangle is congruent to an angle of the second triangle. So we know we have one set of angles that are congruent, and I've got those marked in the picture as well. Then, and if the lengths of the sides including these angles are proportional. So here, instead of needing all three sets of sides proportional to in the same ratios with the other triangle, here I'm only looking at two sets. Okay? And they have to be the two sides that are including this angle.
Hence the side angle side
Exactly.
idea.
So I want to make sure that it's GI and IH. These sides are going to be in the ratios with JL and KL to be able to talk about these pieces being proportional. So I want to make sure that I'm talking about the sides that are surrounding that angle, or that the angle is included between those two sides. So if we know that angle I is congruent to angle L, and we know that the ratios of comparing HI and KL, so those would be corresponding sides, and GI and JL are going to be equal, so they're proportional, then we can say that the triangles are similar.
Okay. So the three options we have, angle-angle similarity, side-side-side similarity, and now side-angle-side similarity. So we're limited here.
Yeah, we are limited.
Unlike congruence, there was more involved with congruence.
And make sure you always use that similarity mark on there too.
Okay, so really that's what we're going to focus on today. Is all about similar triangles, if they are or not. If they are, then what more can you do with it? So just examples. All right? And we got lots of them for us to practice. Says which triangles are similar. So I have a set, basically three triangles. And when you're talking about deciding which triangles are similar, you're probably going to talk about two at a time.
Right.
Okay. Now, what are you noticing about what I'm providing you in all three of these triangles?
Well, I noticed that on all three of these, all we have is side lengths. So I'm probably going to be looking at, can I use side, side, side similarity to say that some of these triangles are similar?
So really, the question mark is, do we have corresponding sides that are proportional?
Right.
Okay. So that's kind of the key. Do we have all three sides, corresponding sides, proportional? Okay.
Right.
So let's just do two at a time. So we'll do the first two here. Now, how do we know which sides are corresponding?
Well, I'm going to go back to the idea of the longest side of one should correspond with the longest side of another, and the shortest side of one should correspond with the shortest side of another.
Because how they're drawn doesn't necessarily mean that's how it matches up. For example, this KL may not actually match with the TH.
In fact, it doesn't, because I know that KL is the longest side of one. That should correspond with the DT, which is the longest side of that next one. So I'm going to say 18 over 30.
Now, guys, you don't necessarily have to write the name of it, but it's going to help if we have some similar triangles. It's going to help with writing the similarity statement, which we're going to practice here in just a minute.
Exactly.
Okay? So when I go ahead and simplify that down, that is, what, 3 over 5?
Mm-hmm.
Okay, so if all the remaining two corresponding pairs have the same ratio of 3/5, then we can say these triangles are similar. So let's keep moving on.
Okay, so then let's check, let's do their shortest sides.
Okay.
So let's do LM is the shortest side, should correspond with the HD because that's the shortest side.
So these kind of match up here.
So 6 over 10, which does simplify to give me 3 over 5.
Okay, looking good so far, but we still need a third pair for this to work.
Okay, so then let's check the middle one. So KM is going to correspond with HT. And KM is the 15, HT is the 25, and divide both by 5, so 3/5, yeah. So these sides are all proportional because they're all the exact same ratios. So I know that those two triangles are similar.
Okay, so since they all have the same ratio, they're proportional, like you said, so we can go ahead and say these triangles are similar. Now, I know the directions don't say write the similarity statement, but it says which triangles are similar, so that basically means let's write our similarity statement. So why don't we do that?
Let's do that. So triangle, let's call the first one LMK. Now I'm going to notice I went through the shortest and then through the middle and then through the long, kind of when I was naming those sides. So this time I'm going to need to say DHT.
And you can always double check. Remember, and we've had this conversation already. I know I've said this with some of my students in class. How you name the first one really doesn't matter. It's how you name the second one.
Right.
So, like, when I look back at here, I notice LM and HD should compare. Okay, so that looks good so far. MK and HT. MK and HT. So it's matching up. All right. If they said Y, which they're not saying, but
that would be side, side, side similarity. Because all three sides of one were proportional to, or were in the same ratios with all three sides of the other.
Okay, let's compare. We still have this one we need to look at.
Yeah.
So let's compare these two now.
Okay, because you can only do two at a time. All right, so let's say, let's see, NP is the shortest side. I'll start with that. And I'm going to go ahead and, that would correspond with the HD. Now, the order that, if you did HD over NP, the order of those won't matter. We're just comparing them. As long as you, since I started with the NP, I always want to put this piece from that smaller triangle first.
Okay.
Okay, so that's 3/10. Now let's look at the longer sides. So let's say DT should correspond with NQ. So 30 over 7, or sorry, 7 over 30. I just totally wrote that backwards though, Mrs. Palermo. We need to flip that around.
We do.
I just said it.
Did you guys notice what she did, everybody?
I just said it and then I did it. So because I started with the NP, I need to start with the NQ on that triangle first. Because I always want to keep the same. I love how I did just try to point that out. Okay, which is going to give me my 7 over 10. 7 over 30. Sorry, I was looking at the 10 that was underlined and just 3. 7 over 30, and that doesn't simplify either.
Okay.
And those are not the same ratios.
So if those ratios aren't the same, it doesn't matter what the third ratio is, because these aren't going to be similar, right?
Right. There's no way, because not all three sets of corresponding.
These two aren't similar. So, okay, what if, so this triangle, this middle one, is not similar to the third one on the right. What about the first and the third? Do we need to check those?
Well, if the first two are similar, then there's no way. If the third one is not similar to the second, then it cannot be similar to the third either.
Exactly. So we're technically done. Now, what if we found these last two were similar? Well, then all three triangles are similar.
So really, once I've kind of done just a couple pairings, I'll be able to make a conclusion with all of them.
And guys, this is kind of, in a sense, like it's not a counterexample, but as long as you show it doesn't work, you don't need to keep going.
Right.
Okay, so just kind of keep that in mind.
All right, next one. Question says, are these triangles similar? All right, so first of all, I've got two triangles on here, and I've got a bunch of information off to the side, so let's mark our picture.
Okay.
Okay, so we know that AC is 6. And we know that AD, so going all the way down here, is going to be a 10.
Okay.
And we know that BC is 9. And then BE, this whole big thing here, is going to be a 15. Now, because I'm comparing triangles, I might want to talk about the pieces of this other triangle, right?
Yeah, because the BE and the AD are not actual sides of a triangle. So really, comparing that wouldn't really help us out.
Right.
But I know since AD is, the whole thing is 10 and part of it is 6, so DC is going to be 4. And then the same deal with the others, that's going to be 6.
So really, you're using a little segment addition postulate there to be able to do that. I'm going to go ahead and just take off the other pieces for right now that were the larger segments, because what we're trying to do is to look at the triangles and determine if the triangles are similar.
Yeah, that makes sense.
Okay. Now, looking at this, what theorem or postulate are you kind of leaning towards?
Okay, well,
helping us to do this.
Again, our options: angle similarity, side similarity, and then side similarity. Now, I notice in the picture there's sides labeled, and there's 2 sides labeled in each. So I'm probably going to lean towards the later two, the ones we learned about today.
Right.
Now, side similarity would mean we'd have to know something about ED and AB, and I don't know, and I can't figure it out. So that's probably not going to be an option. And again, we don't know if these triangles are similar. I'm just kind of thinking if they were, what approach. So the only way I could show that these are similar is if I could use side similarity. And so I see in the picture, hopefully you see the same thing, some vertical angles. So angle ECD is going to be congruent to ACB. Now, does that guarantee these triangles are similar?
No, it just allows us to have an approach.
Okay, so I still got to check if the sides are proportional, right?
Exactly.
And more specifically, the corresponding sides. Okay, keep that in mind. So kind of using the approach Ms. Hochgrabe did on the last one, when you're comparing the sides, make sure you match up kind of based on the length. So I'm looking at that triangle ECD, and out of the 2 sides they're giving you, the 6 and the 4, the 6 is the longer of the 2, so I'm going to compare it with the longer of the 2 the other. So EC compared to CB. Okay, obviously some people might think compare EC to AC, and you don't want to do that. No. Simplify that to 2/3. So if the other set gets you the same ratio, then we can say they're similar. So DC to AC or CE, CA, whatever. So 4/6, which is also 2/3.
So here you had one set of angles that were congruent, and it is the included angle. It's between the 2 sides. And you had those 2 sides that were including that angle were proportional.
Okay.
So we can say that.
So yes, they are similar. Now, it doesn't say anything extra, so technically we're done, but I know that we're probably going to ask you to write what kind of things.
The similarity statement.
So let's do that. So triangle ECD is similar to triangle BCA. And they might say, what's the reason? Well, side similarity.
Love it.
All right. Notice up here, they give you a proportion, which basically is 2 ratios that are equal. All right. And the first question says, why is triangle PBA similar to triangle PDC? So essentially, since they're saying why is this happening, that's saying they are going to be similar.
Okay.
We're just explaining why. So looking at the picture, there's really nothing labeled, okay? And here's the deal, guys. Labeling proportions, you're not like labeling congruent stuff.
Right.
Okay?
So you can't use little tick marks.
No. So it's not necessarily the easiest to label, all right? Sometimes it helps to maybe redraw the 2 triangles, all right? I might do that just so you kind of have a little visual here. So I'm going to put it in the order they gave you. So here's the P, and I'll do B. A. My stomach just growled. Sorry. I don't know if you guys heard it.
You never know.
I know. So P, and then I went DC. Okay. So they're telling you, let's look at it. PB to PD.
So those are corresponding
This
pieces.
side
It's kind of what it
to
sounds
this
like.
side is equal to PA to PC. Okay?
Okay, so we really do have two sets of corresponding sides that are in a proportion to one
Okay.
another.
But in order to say that they're similar, which they're saying, we're trying to decide, we either need another side or the included angle, right?
Right. Well, since obviously they don't give us anything about the side.
Mm-hmm.
But I do notice that they both have angle P. So they share that common angle. So they do have that included angle as congruent.
So what's my reason?
So side, angle side, similarity.
All right. Moving on. Part B gives you some stuff to label. I'm going to label, and again, you don't have to redraw the picture. I'm going to label the original picture, and then maybe if we need to go to this, we can do that. All right, so PA is 8 inches. AC is also 8 inches. BA is 1.8 inches. And the question mark is, what's DC's length?
Okay, so if we already know that these triangles are similar now,
Yeah.
then we can look at any set of corresponding sides because we know all corresponding sides will be proportional. So,
I want to make a note of that. She said corresponding sides, and I'm going to underline that.
yes. So, I know the most common mistake is I will have somebody, Mrs. Palermo, that will want to write the ratio of 8 over 8 equals 1.8 over x.
So you're comparing, essentially saying PA to AC is the same as BA to DC. What's the wrong with that?
Well, because, and I love that you underlined sides, because AC is not a side. And like I said, that is the most common mistake people will make. They'll see the separate parts labeled in the picture, so they'll just want to use those separate parts. So be careful. And I love that you redrew the picture because I think that that's a great visual. If we mark that picture, PA is 8, and PC, we don't actually have marked on our original picture, but it would be 16 if you add those two sides together. And then our 1.8 and our x. So our actual ratio, or proportion. Should be 8 over 16 equals our 1.8 over DC.
And this brings up again a conversation. We've said this before. If you want to label this X,
That's
just be
fine.
careful, okay? In this case, X is DC, and what's the question asking
That's
for?
what you're solving for,
So
is
you
DC.
can put X as long as that's the thing you're finding, okay? Or you remember that. But the other thing to keep in mind is if there's multiple things you're finding, you can't use the same variable. So this is one case where using X would be completely fine.
Be fine, sure.
All right? So when you go ahead and cross multiply, so I have 8 times the DC, or you could have X, equals, what's 1.8 times 16?
28.8.
So DC is equal to,
3.6.
and this is inches. Now, think about would this be logical if I said this is 3.6?
Well, yeah, actually, I'm looking at 8 and 16. It's doubled.
Yeah.
Right? 16 is double 8. So 3.6 is double the 1.8. So yeah, that makes perfect sense. All right, next one. It says we're going to find the distance across the river. Now, Mrs. Palermo, if you were trying to make it across a river, what is the shortest distance across a river to be able to go?
Well, and you want to do shortest because there's no way I'm going to like swim across long ways. I'm, smart about this. I would go more that vertical, that perpendicular distance.
Yeah.
We've talked about that before.
We've talked about that before. So this is really what we're looking for. When we say distance across the river, we know we're talking about the perpendicular distance across that river. Now, notice we've got two triangles. What do you notice about these two triangles?
Well, I'm thinking they're probably similar because that's what we've been talking about.
Probably.
But I noticed they're both right triangles, so they do have congruent right angles, and they also have vertical angles, and so those are also congruent, which basically means you can prove these triangles are similar by angle-angle similarity.
Exactly.
So now I can set up a proportion.
Right.
Okay.
You do need to know that you have similar triangles before you start setting up proportions. They'll either give it to you or give you enough information in the picture if that's what you're supposed to be doing. Hopefully.
Yes.
Okay. All right. So what am I going to do to find this missing piece then?
Well, since they're similar triangles and the stuff that's labeled and what we're trying to find involve the sides, we're going to set up a proportion. So I'll say 42, so that's the 42 feet. I'm going to compare that to the 8. Both of those are kind of that horizontal distance, but also I notice that that's kind of across from that vertical angle, so you can see that as well. Then I'm going to say X because I don't know, so you might label that in the picture so we know that's what we're trying to find.
Great idea.
Over 5. So a little cross multiplication, so you get 8x equals to 10, and x says 26.25 feet, which is essentially 26 and now a fourth foot.
A fourth of a foot.
Now a fourth of a foot. A foot has 12 inches in it, so a fourth of 12 inches would be 3 inches. So it would be 26 feet and 3 inches.
And guys, keep in mind, something like this, you'd probably want to go ahead and convert to talk about feet and inches because we don't use fraction or decimals with feet. We do talk about feet and inches. So if you need to, take that 0.25 in your calculator, and you can always take it times that conversion factor. That in this case, there's 12 inches in a foot.
So you would just multiply it by 12.
Yeah, or a fourth of 12, just like Mrs. Palermo thought it in her head. Love it.
Now, this is actually a pretty popular type problem you may have done before. This actually, if you look at it, I don't even see triangles. So I'm going to kind of give you a visual of why this is involved with this particular lesson. It says, what is the height of the flagpole? So in this scenario, what you're doing, and it kind of goes along with the last one, we're going to measure the height of this flagpole indirectly, meaning we're not actually going to go to the top of it and drop like a ruler or whatever.
Not be a long ruler. Maybe tape measure, but
tape measure still. I don't want to climb up the flagpole. Either. Okay, so we're going to indirectly measure by doing things that we can easily measure. So we measured the height of this stick figure. Okay,
our beautiful artistic abilities.
And we also measured the shadow of that stick figure. That's easy to do. For the flagpole, we just measured the shadow, which is again easy to do. So what I want to keep in mind is the shadow is measured at the same time of day. And why this works, if you kind of get a visual of this, my artistic ability here, right? So here's your sun up here somewhere, okay? And when you measure your height, you're going to be perpendicular. You're not going to be slouched over. You want to actually have the actual measure. And I do that same thing with the shadow or the flagpole, right? This angle is going to be the same degree because it's the same time of day. And then you have a right angle because it's perpendicular ground, which means the triangles are similar.
Perfect.
Right? So let me label the stuff in here, and you talk to me about some things that you're noticing.
Well, one thing I notice is I've got feet and inches all in the same, within heights, shadows, and everything. And so we're probably going to want to convert that so that way they're all inches because I can't really cross multiply with feet and inches.
No.
So I'm going to say like the first one, the person's height, our beautiful person's height, is 67 inches. And I get that by taking, 5 feet, there's 12 inches in a foot. So 5 times 12 is going to give me the 60 and add the extra 7, so 67.
Okay.
The shadow is going to be 50 inches. And the next shadow of the flagpole is going to be 150 inches.
So if you think about it, really what's going to be helpful are these. So I'm going to go back and label. This is really what we're going to use. All right?
Okay. And I noticed that I'm trying to find the height. So let's go ahead and set up our proportion because these are similar triangles. You said that angle up at the top is going to be congruent, and we know the right angles are congruent. So we know angle similarity. These are similar triangles. And so we're going to write 67 corresponds with the H.
The height of the person, the height of the the height of the flagpole.
And the 50 corresponds with the 150.
So shadow of the person, shadow of the flagpole.
Exactly.
So do a little cross multiplication.
We get, 50x will equal 10,050.
Or 50h in this case, since I used an h.
Oh yeah, sorry.
It's okay.
And then therefore h is going to be 201 inches. Now, I wouldn't just say something's 201 inches. I don't usually measure in inches. And obviously, looking back at the original problem, they didn't either. So to convert that into feet and inches, well, if I divide that by 12, that's going to give me 16 whole feet. And then I would be left over with 9 inches. Okay. Next one. This one says determine if the triangles are similar. And if they are, then we're going to write a similarity statement and solve for W. So right now, we don't even know that these triangles are similar. So the first thing that I see is I've got some triangles here that overlap. So what should I probably do first?
Let's redraw them. And guys, while she's redrawing them, to me, I mean, bottom line in this one, I definitely redraw, because how they're drawn doesn't show the correspondence necessarily. Sometimes they do, sometimes they don't. Again, I want to stress the fact what Ms. Hokery said. We don't know if these are similar. So we can't just go jump and say, okay, I can find W by using setting proportion. We don't know if these are similar. So we got to determine that first.
And notice over here, too, that I did a little just segment addition postulate.
Yep.
Because we had a 7 and a 6, so obviously I know the whole thing's going to be 13. And I had a 37 and a 2. So when I'm labeling these, I'm taking all of that into account.
Okay.
Okay. And then this right here is my W. So the first question is, are they similar?
Yeah. So again, we can't set up that proportion. And I know that's what I see people do in a problem like this. So we got to first decide if they're similar. And since, here's the deal. I don't know AE, the side of that larger triangle. I can't decide if these are by side similarity.
Right.
And since I have sides in it, I probably am leaning towards the other one dealing with sides, so side angle side, which means I'd have to know an included angle. And so I'm thinking, and I noticed that they both have angle C in common. So those would be congruent.
Right, because it's the exact same angle.
Yeah. So then let's talk about the sides that surround that angle, because it has to be an included angle. And again, I got to match up corresponding sides. So like in the larger triangle, AC is the longer of the two sides that surround it. And so I'm going to compare it to DC, which is the longer of the two sides.
Right. So that's going to be a 39 over
9, or 6, sorry.
6, that's okay.
So that would be 13 over 2.
All right. And then the other set of sides that I'd want to compare would be?
So now I started with the top triangle, or the bigger triangle, so EC to BC. So that is simplifies to is 13 over 2, which is simplified already. So those are the same, and we have the included angle. So yes, these are similar.
Okay.
So it says if they are, give the similarity statement.
So triangle, what do you want to name the first one?
Let's call it ACE. And I'm going to call the second one, what, DCB?
Okay. And again, watch how you name them. Watch the order that you name them. Because you started going towards angle C, but through the larger side and then the smaller side, we're going to do the same thing here. So going towards angle C, through the larger side, then through the smaller side. Now, if they are, we're supposed to write the similarity statement and solve for W.
Okay, so now we know that they're similar, which means we can set up a proportion.
Because all the corresponding sides will be proportional.
Now, we've already stated 2 the ratios, and notice they both simplify down to 3 to 2. So I'm just going to, or 13 to 2, sorry. I'm going to use that. That's our scale factor, essentially. Now, the 13 kind of goes along with the larger triangle, so I'm going to say equals W over 5, since those two sides correspond as well.
Great. And yeah, you could have said that was EC over BC and EA over BD, or you can always use your scale factor there too. So when you cross multiply, you get 2W
equals 65. So then you get 32.5.
Love it. And that's what they asked. They asked for W. They asked us to write our similarity statement, which we did. The only thing they didn't ask here is what theorem or postulate did you use, and what did we use?
Side angle side similarity.
Side angle side similarity, yeah.
Yep. Last one. Says just find X.
Okay. Which, I'm guessing these are maybe similar triangles.
Probably so.
And looking at the right angles that are marked there, we know those are congruent, and we do have that included angle up at the top that's congruent. So let's do this. Now, I'm going to suggest let's maybe write these separate, draw them separately.
And when would that be helpful? Bottom line, it's when the triangles kind of overlap. We've done this with congruent. I love this suggestion. Let's label. So in this triangle, we know this is the 5, this is the 7.
Yeah, 7.
What about the larger triangle?
Well, we need to add those two together, so x plus 5.
Now, why not 5x?
Well, because that would be if I'd multiplied them together. That's a common thing we'll see, though. So x plus 5 and then the 16.
And again, notice this x is not an actual side. So you're not going to say 5 to x,
right?
7 to 16, because that x is not actually a side.
Right.
So we need a sub proportion, so help me out.
So let's do 5 over x plus 5 is equal to 7 over 16. And so we're going to get 7x plus 35 equals an 80.
I'll make a little note. That's where that's coming from. You don't have to show that.
And then when you subtract a 35, you get a 45. And when you divide by 7, we're just going to leave it as 45/7 because it doesn't give us a nice pretty decimal. It gives us a decimal. It's just not a whole value. So we'll just say 45/7.
Perfect.